You so
This meeting
much.
is recorded.
And thank you so much for including me in this seminar. And I took this picture just a couple of weeks ago when Ryan and my daughter and I were hiking out of Grand Canyon and a snowstorm was rolling in. And I was really grateful for the snow, but looking around on the Bright Angel Trail, it was pretty clear that many visitors from other places were not prepared to have a cold and snowy day on their trip to the desert. But it also occurred to me that they might also not be able to really see the impacts of the drought conditions that we've been having for most of the 21st century because they come to this region expecting dry conditions. I am an assistant research professor at Northern Arizona University, and I study land-atmosphere interactions in drylands around the world. I am an atmospheric scientist by training. And before I start, I want to acknowledge that Northern Arizona University sits at the base of the San Francisco Peaks on homeland sacred to Native Americans throughout the region. And we honor their past, present, and future generations who have lived here for millennia and will forever call this place home. Drought in the Southwest is a symptom of global climate change. And I want to put that climate change into context. And I think Dave Worthington also talked about climate change in this region. And I want to do that by showing this animation from NASA, which puts what we're experiencing into a global context by visualizing global temperature anomalies, which are the differences between a measured or modeled temperature and some kind of long-term average, in this case, the average of temperatures between 1951 and 1980, or the middle of the 20th century. You can keep track, as I set this animation going, you can keep track of time by looking at the top. And so here it's showing the average global temperature anomalies from 1880 to 1884. And you can keep track of the anomalies by looking at the scale bar over here on the left. But in general, if you see cool colors like blues, that means that the temperatures were below that mid-century average. And if you see oranges and reds, it means that they were above average. So you can see in this first view that most of the world was in fact cooler than the mid-20th century average at the start of the Industrial Revolution, but that's not uniform and it's not true everywhere. So I'm going to get this animation going. And as we're going through the end of the 19th century and into the early 20th century, the globe is mostly blue, indicating that the temperatures were generally below that mid-century average. As we get into the middle of the 20th century and then into my lifetime, starting in the 1970s, you see a lot more yellows and oranges. And then I want you to notice as we get into the 2000s, the globe is a little bit more uniformly orange and red. And here we are in the southwestern US, even though the globe is mostly in the oranges and reds, it's not uniform. And our temperature increases are not the same as, say the poles, which are increasing, where temperatures are increasing at a more rapid rate. The main global control on our climate is global circulation. The Earth is basically a tilted spinning ball of fluids, if you're an atmospheric scientist like I am. So it's not heated evenly. This is a generalized view of the Earth as an aqua planet where there aren't any continents to get in the way. And these red colors at the equator of this aqua planet indicate that the planet is warmed more at the equator than at the poles, where it's shown in blue. Even without continents, you can set up dry regions 30 degrees north and south of the equator, which is where we see dry lands globally on our real Earth. And that happens because this warm air at the equator sets up a low pressure here. So air rushes in towards the equator from both north and south of the equator, and it's bent because the Earth is rotating. As that air rushes in, it picks up evaporated water vapor from the surface of the ocean. And then as it meets at the equator, the air rises in what are called Hadley cells. And that warm, wet air rising starts to cool. As the air starts to cool, there are huge storms that form as the water vapor condenses. But then the air that ends up descending or subsiding back to Earth at 30 degrees north and 30 degrees south of the equator ends up being drier. And that's what sets up a situation for these global drylands. From an atmospheric perspective, it's pretty clear that the Hadley cells are expanding and getting drier. And so that is potentially expanding the extent of drylands around the world. But let's look at where they are now. We don't live on an aquaplanet, but that global desert belt predicted by atmospheric circulation still exists. The southwestern US lies in this region of global drylands that's clearly visible on a satellite image. But topography and the variability in local temperature and moisture seen at different elevations have major impacts on how atmospheric dynamics and global change translate into the diverse ecosystems we see in drylands. So I just put up some pictures here of some drylands around the world. Here's a picture of Grand Canyon in our southwestern US, but it looks pretty different from Ethiopia. The Atacama Desert has barely any vegetation off the coast of South Africa and in Australia. Today, I'm going to focus on drought impacts on the southwestern US and our ecosystems in the Colorado Plateau, where we are in the midst of a multi-decadal drought that has led to vegetation mortality and changes in ecosystem distribution. It also has a major impact on the amount of water available for the river, but I believe that Dr. Udall will be likely addressing that in detail next, so I'm not going to speak about it in my presentation. Climate is by definition based on long-term average conditions, and the ecosystems we see around us are adapted to those long-term average conditions. Dave Worthington earlier showed a time series of temperatures around the South Rim. I'm going to show those temperatures and precipitation trends a little bit differently in these graphs. So over here on the left, I'm showing the long-term average precipitation approximately at the South Rim in each month. So the months are shown on the x-axis, and then that average precipitation in bars on the y-axis. Over here on the right, I'm showing average temperatures for those same pixels in the long term. And I based these graphs on 128 years of data. I want you to notice a couple of things about the temperature and precipitation monthly trends, because that's what our ecosystems are adapted to. First of all, our ecosystems are adapted to precipitation peaks in the winter, December, January, and February, and in the summer when the North American monsoon brings moisture to our region through thunderstorms. So that's shown here in kind of July, August, and September. Our ecosystems are also adapted to cold temperatures in the winter. So if you notice that the average temperature over that 128-year record was below 0 degrees Celsius. And then in December, it doesn't even look like there's a bar there because the average temperature is around 0. Also, our ecosystems are adapted to dry and warm conditions right before the monsoon hits in June. So I want you to keep in mind these long-term average conditions, and I'm going to superimpose the 21st century on that, so since the year 2000. So the purple bars are now showing the averages over the last 22 years. So over here on the left, that's still precipitation. The light blue that's still peaking out is the difference between the 21st century and that longer term average that I showed before. And in all months, basically, there is lower precipitation with the exception of October. Over here on the right with temperatures, the darker orange is showing that difference between that long-term average, the long-term average temperatures in each month and what we've been experiencing since the start of the 21st century. And I think it's really important to note a couple of things. First of all, the January temperatures on average have been above 0 since the year 2000. Same is true in December. And that's coupled with lower than that long-term average precipitation. And that means that there's less water coming into the system and it's sticking around a little less, because if it comes as snow, it's more likely to melt faster. It's less likely to even come here as snow. And that sets up a situation for our ecosystem that's not all that great. Typically, winter precipitation is credited for recharging soil moisture that a lot of the ecosystems on the rim and around the Colorado Plateau use. And so if you have a ponderosa pine forest like we have here in Flagstaff, typically based on a lot of studies that have been done using isotopes in water, typically the water that those ponderosa pines are using is winter precip. So if that winter precip's not coming in and recharging the soil moisture, those ecosystems don't have that moisture to use in the summer. Speaking of the summer, that dry time in June is seeing less precipitation. It's also seeing higher temperatures, and that is putting more stress on those ecosystems during their growing seasons. Just like in the global temperature anomaly animation I showed before, those changes in precipitation and temperatures are not uniformly distributed either in time or space. If you notice across the top, I've got precipitation anomalies in these 3 panels across the top for winter in 2019 to 2020 through this most recent winter that we're just coming out of, 2021 to 22. Any area that you see, and these are just maps of our region. I've got the Colorado River basins outlined in bold, and here's Flagstaff. Any purples that you see mean above average precipitation. Any browns you see were below average precipitation. On the bottom, I've got the same maps, but now for temperature anomalies or difference from average conditions. Here, any reds you see are above average and any blues you see are below average. So if we look at this most recent winter, there was some above average precipitation in parts of the upper Colorado River Basin, but those were also coupled with above average temperatures. So that's the most recent winter. If we look at the monsoon conditions, these are the same maps, but now for July, August, and September. So again, in this upper row, if you see browns, that means below average precipitation for those months. And down in this lower panel, if you see reds, that's above average temperature. So let's just look at the 2021 monsoon for simplicity. Over here on the far right in the top row, there was above average precipitation during the monsoon last year, and that did provide some relief for drought-stressed plants. However, it was also coupled with higher temperatures, so it did not provide as much relief as it could have. So what does that end up looking on our landscape? Well, one major impact of climate change on southwestern landscapes is tree mortality. And it's a striking drought impact and very obvious to people who live here. So what I'm showing here is a picture of the pinyon die-off from 2002, when there was a major pinyon die-off across the region. The pictures are from northern New Mexico from a paper by Craig Allen, but I'm sure that anybody from the Flagstaff area recognizes this scene from when the pinyons died off. In the upper view, they're all the brown pinyons. And in this case, the direct cause of death was not actually drought, it was bark beetles. But drought set up the conditions that led to the mortality. Warmer winter temperatures increased the bark beetle population, and then high temperatures and decreased precipitation increased the stress on the pinyons during their growing season. And the drought-stressed pinyons couldn't fight off the beetles and ended up dying across the entire Colorado Plateau region. Several ecosystems changed from pinyon juniper woodlands to juniper savannas, where the only woody vegetation around is juniper. And that happened over the course of just a couple of years. So if you look at this top panel, that's 2002 with the pinyon die-off. And then at the bottom panel, the only green left is junipers rather than pinyons, and all the gray is dead pinyons. We're seeing a similar situation right now in the Flagstaff area, and in 2018, this happened up in the Bears Ear region in Utah, where we're seeing juniper mortality. And that's a little alarming. Pinyons are a little more sensitive to drought than junipers are. Junipers are quite drought resistant plants. This is a picture that I took last May off of 89 just outside of Flagstaff. And I'm not as good a photographer as Craig Allen, but if you look across the entire area, all the brown you can see are dead or dying junipers. I didn't get a picture of it, but when I went back after the monsoon started, some of those junipers, you know, they can just be putting water into specific branches. So you might see like a half dead juniper, but some of those junipers did look like they were coming back, but many of them have died at this point. According to some preliminary studies that have come out, the mortality is not related to beetles this time. It's certainly not related to a single dry season. These are quite resilient plants, but instead the mortality is a direct result of the dry and hot conditions that have characterized the 21st century across the Colorado Plateau and the cumulative effects of drought on these ecosystems.
We've got about 2 minutes, Kimberly.
Thank you. Drought impacts on riparian vegetation along dam-controlled rivers are highly variable, and they depend on flows and sensitivity of the species. Since I am limited on time, I'm not going to go into detail here, but if you have an area like this on the Bill Williams, where you have a lot of cottonwoods, the cottonwood trees are extremely sensitive and can really die when their roots are out of the water. So a simple view is that as long as there's enough water moving through the dam in a dam controlled river to maintain the water table, the plants don't really care if the air is dry because their roots are in water. Cottonwoods aren't super common in Grand Canyon, and the riparian species that do grow along the shores are less sensitive than cottonwoods. So many of them propagate clonally or have less finicky seeds. So if the water table drops rapidly and leaves their roots exposed all at once, then they will in fact die. But if those declines are gradual, most of those species will follow the dropping shorelines. So that encroachment is not likely to end as temperatures increase and precipitation decreases. So drought conditions appear to be with us for the foreseeable future. This map is from NOAA's Spring Outlook, which was published just last week. And the yellows and browns that cover most of the Four Corners region indicate that drought will be developing, continuing, or worsening across most of the region, and we'll continue to see impacts on vegetation and water as the drought continues. That map's a little too depressing to leave up, so I want to leave you with this picture instead of a summer thunderstorm on the river. And I'm hoping that as you float the Colorado River with passengers this season, I hope you'll take the opportunity to talk to them about climate, whether it's in terms of the ancient climate that's preserved in the sedimentary rocks that you see along the river, or what you would expect to experience on the trip and how that compares to the long-term conditions that we all know as residents of the southwestern US, and how our landscapes are changing as a result of those changes. So thank you very much for your time. And I really am very grateful to this group for allowing me to speak today.
Kimberly, thank you very much for your photography, your information, your science, and for being with us today. Thank you.
Thank you.